In December 2024, at the American Geophysical Union Conference in Washington, D.C., scientists made a prediction, rare in volcanology. Not that a volcano might erupt, not that an eruption was possible, but that Axial Seamount, an underwater volcano 300 miles off the Oregon coast, would erupt before the end of 2025. They were specific. They were confident. They were wrong. December 31, 2025 arrived. The deadline passed. Axial Seamount, sitting 1,400 meters below the surface of the Pacific Ocean, refused to cooperate. The most monitored underwater volcano on Earth, surrounded by 150 real-time sensors connected by fiber-optic cables, had defeated the best prediction science could make. This is not a mystery volcano in an unexplored ocean. Axial is comprehensively instrumented. Pressure gauges measure seafloor inflation to millimeter precision. Seismometers detect every earthquake. High-definition cameras watch hydrothermal vents where superheated water supports entire ecosystems in complete darkness. A monitoring network that costs $386 million represents humanity's most ambitious effort to understand volcanic behavior. Scientists at Oregon State University and the University of Washington had every reason to be confident. Axial had erupted 3 times in recent history: in 1998, in 2011, in 2015. Each time the pattern was identical. The seafloor inflated by specific amounts. Earthquake swarms intensified, then eruption. By November 2024, Axial had surpassed the inflation threshold that preceded the 2015 eruption. The pattern seemed to be repeating, except it did not erupt. This is not a story about a volcano that might erupt tomorrow. This is a story about how the most monitored volcano on Earth, with the best data ever collected, defeated the best predictions science could make, and what that failure reveals about our ability to forecast geological events that could, in other locations, kill millions. To understand why scientists thought they could predict Axial Seamount's eruption, you need to understand what this volcano actually is. Not just an underwater mountain, but a geological laboratory that has transformed our understanding of submarine volcanism. Axial Seamount sits 300 miles west of Cannon Beach, Oregon. Its summit lies 1,400 meters below sea level. The volcano rises 1,100 meters above the surrounding seafloor, crowned by an oval crater measuring 3 by 8 kilometers. It is a mountain beneath the ocean, formed by a mantle hotspot sitting directly on the Juan de Fuca Ridge, where tectonic plates pull apart. The combination is unusual. Hotspot volcanoes typically form island chains like Hawaii. Spreading ridge volcanoes typically produce gentle seafloor lava flows. Axial is both, making it the most active underwater volcano in the northeastern Pacific Ocean. Documented eruptions occurred in 1998, 2011, and 2015. The intervals tell a story. 13 years between the first and second eruptions, 4 years between the second and third. The pattern suggested accelerating activity. In 2014, the Ocean Observatories Initiative Regional Cabled Array became operational. 900 kilometers of fiber-optic cables sprawled across the seafloor. 150 instruments delivered continuous data. The system cost $386 million. This was total surveillance. The instrumentation is extraordinary. Bottom pressure recorders measure seafloor uplift to millimeter precision. Seismometers detect earthquakes as small as magnitude 0.5. High-definition cameras provide live feeds of hydrothermal vents where superheated water supports ecosystems that thrive without sunlight. William Chadwick, a research associate at Oregon State University, maintains the Axial blog, a public chronicle of the volcano's every movement. The data is transparent. The monitoring is total. And still, the volcano surprised us. The 2011 and 2015 eruptions, established a pattern. Seafloor inflation reached approximately 2.4 meters before eruption. Earthquake activity intensified to thousands of events in the days preceding lava flows. Both eruptions followed the same sequence, same inflation threshold, same seismic escalation, same result. Scientists published papers announcing that submarine volcano eruption forecasting had entered a new era. Pattern recognition from 2 data points. It seemed sufficient. From 2015 to 2023, axial inflated gradually, but the rate declined. By summer 2023, inflation had nearly stopped. Then fall 2023 arrived. Sudden reawakening. Inflation rates increased. By January 2024, the rate reached 25 centimeters per year. It looked exactly like the behavior before the 2015 eruption. November 2024 brought the milestone. Axial surpassed the inflation level that preceded the 2015 eruption. Scientists assessed the volcano as primed. At the December 2024 conference, Chadwick presented his forecast. Axial Seamount has woken up and is building toward its next eruption. Our current eruption forecast window is between now and the end of 2025. Media coverage went global. The prediction was specific. The confidence was high. Then 2025 unfolded. Month by month, as the volcano refused to erupt, scientists confronted a reality that no amount of instrumentation could change. January 2025 began with optimism. Inflation continued. Seismic activity remained steady. Every week, Chadwick updated the Axial blog with new data. By summer, media outlets revisited the story. The world's most monitored volcano was approaching its deadline. March arrived. Still no eruption. Then June brought a brief earthquake swarm. More than 2,000 events in one day. Automated alerts triggered. Scientists thought an eruption was imminent. It was a false alarm, caused by tsunami waves from a magnitude 8.8 earthquake near Kamchatka, thousands of miles away. The volcano itself remained quiet. July brought concerning news. Inflation rates began slowing. By October, the rate had dropped to 10 centimeters per year, half what it had been. On October 26th, Chadwick updated the blog with a candid admission. It is starting to feel like our latest eruption forecast is running out of time. The problem was clear. The inflation rate was lower than anticipated. It will take more time than we anticipated to reach the same inflation threshold. The volcano was not following the script. On December 16, 2025, Chadwick presented his updated analysis. New forecast. Sometime in 2026. He was remarkably candid. This whole thing has been an experiment to see how far we can push the envelope of long-term eruption forecasting. Part of that is learning from experience what is possible and what is not possible. The prediction failed because scientists made 3 critical assumptions that proved incorrect. First, they assumed the inflation threshold remained constant at 2.4 meters, but deeper analysis showed the threshold actually increases slightly with each eruption. When magma rises and erupts, it compresses the surrounding crust. This makes subsequent eruptions harder. Each cycle requires slightly more pressure buildup. Second, they assumed inflation alone triggers eruption. But seismicity may be equally important. Before the 2015 eruption, Axial experienced sustained periods exceeding 2,000 earthquakes per day. In 2025, typical daily seismicity was only 200 to 300 earthquakes. Sustained high activity never materialized. The volcano needs both an inflation threshold and a seismic threshold. One without the other is insufficient. Third, they assumed patterns from 2 eruptions constitute a reliable forecasting framework. They do not. 2 data points make a coincidence, not a pattern. Volcanic systems are complex. Processes occur deep in magma chambers that cannot be directly observed. Dr. Deborah Kelly, director of the Regional Cabled Array, stated it plainly. Volcanoes are complex systems. We are measuring everything we can measure. We have the best data that has ever existed for any underwater volcano. And still, the behavior is not perfectly predictable. When the forecast went public, some media outlets were sensationalized. One headline declared the underwater volcano was going to blow. Chadwick responded, "Any story that starts with how it is going to blow raises a red flag. It is just not that kind of volcano, and it gives the wrong impression." Another outlet claimed eruption was inevitable. Chadwick corrected them. That does not mean inevitable. It means eventual. The danger of false precision became clear. Making specific time-bound predictions, even with perfect data, creates false expectations and damages credibility when nature refuses to cooperate. Before examining the implications of this failed forecast, we must correct the record about what actually happens when Axial erupts. The threat level is 0. The official assessment states clearly, the potential eruption is not expected to cause any risk to human life or property and will not create tsunami waves. Bill Chadwick put it simply. For the size of eruptions we have seen in the last 20 years, if you were on top of it on a boat, you would never know it. Why no danger? DEP ETH. Axial sits 1,400 meters below the surface, too deep for surface effects. Distance: 300 miles from shore, too far for coastal impact. Eruption style: effusive lava flows, not explosive. No tsunami risk because lava flows gently on the seafloor. No atmospheric impact because the eruption occurs under extreme pressure. The actual consequences are ecological and scientific, not catastrophic. The 2011 eruption wiped out a hydrothermal vent field. Lava flows killed tube worms, clams, and microbial mats. Recovery was rapid. Within 3 months, new vents formed. Within 2 years, full ecosystem recovery. These ecosystems have evolved with volcanic activity for millions of years. The eruptions are renewal events, not catastrophes. An axial eruption is not a crisis. It is a scientific opportunity. William Wilcock explained why this matters. This is why we built the cabled array, to watch an eruption happen in real time with unprecedented detail. We will learn more from one eruption at Axial than from decades of studying land volcanoes after the fact. But the real stakes extend far beyond one submarine volcano. Worldwide, approximately 1,500 volcanoes are considered active. 500 million people live within potential hazard zones. 29 eruptions occur per year on average. Our ability to forecast these eruptions remains poor to moderate. Mount Pinatubo in 1991 was forecast days in advance. The successful evacuation saved thousands. Mount Unzen that same year saw forecasting fail. Pyroclastic flows killed 43 people. Eyjafjallajökull in 2010 disrupted global air travel and cost $1.7 billion. Cumbre Vieja in 2021 destroyed 7,000 buildings. The axial lesson is sobering. If scientists cannot reliably forecast eruptions at the world's most monitored volcano with perfect data, what hope exists for forecasting at Vesuvius, Fuji, Rainier, or other volcanoes threatening major cities? Some media coverage falsely connects Axial to Cascadia subduction zone earthquake risk. This is incorrect. Axial sits on the Juan de Fuca Ridge, where plates pull apart. The Cascadia subduction zone is 200 miles to the east. They are part of the same tectonic system, but have no direct connection. An eruption at Axial tells us nothing about earthquake risk in Seattle or Portland. In November 2024, scientists began testing a revolutionary physics-based forecasting model developed by researchers in Sweden and Switzerland. Instead of pattern recognition, which failed, the model calculates when accumulating stress will exceed material strength. Early results show promise. The model correctly predicted that 2025 would not see an eruption. If this approach works at Axial, it could revolutionize eruption forecasting globally. This is not a story about a failed prediction. This is a story about the limits of scientific certainty in complex natural systems. Axial Seamount has the best monitoring of any volcano on Earth. 150 instruments transmit real-time data, decades of observations, hundreds of millions of dollars invested, scientists who have dedicated entire careers to understanding this single volcano, and still they cannot predict when it will erupt with precision greater than a one-year window. And even that window proved incorrect. The lesson is not that scientists failed. The lesson is that nature is irreducibly complex. If we cannot forecast Axial with perfect data, how do we forecast Vesuvius with sparse data? How do we forecast Mount Rainier with indirect measurements? Yellowstone with ambiguous signals? The Axial experiment reveals that even perfect observation does not guarantee perfect prediction. Volcanic systems involve processes we cannot directly observe, like magma chamber dynamics, crystal growth, and gas bubble nucleation. Mechanical failure thresholds vary with temperature, pressure, and time. Communities near active volcanoes depend on warnings. Evacuation decisions must be made days in advance. False alarms erode trust. Missed warnings cost lives. The Axial case shows that even with unlimited resources, eruption forecasting remains probabilistic, not deterministic. We can say likely in the next year or two, but not next Tuesday at 3 p.m. Dr. Bill Chadwick's willingness to publicly document a failed prediction is rare in science. Most failed forecasts are quietly forgotten. Chadwick chose transparency, updating the blog monthly with contradicting data. This whole thing has been an experiment. Part of that is learning what is possible and what is not possible. As of January 2026, Axial has not erupted. Inflation continues at 2.5 meters above baseline. Seismic activity averages 200 to 400 earthquakes daily. The new forecast suggests an eruption is likely sometime in 2026. The confidence level is lower. 3 scenarios remain possible. Axial erupts in 2026, and scientists analyze what threshold was actually reached. Or Axial continues inflating beyond 2026, challenging fundamental assumptions about volcanic behavior. Or deflation occurs without eruption, indicating we fundamentally misunderstand the magma plumbing system. Axial Seamount is a test case for humanity's ability to predict geological hazards. We applied every available technology to this volcano. We achieved instrumentation that seemed impossible 20 years ago. We thought perfect observation would yield perfect prediction. Nature disagreed. The volcano sits 1,400 meters below the surface, surrounded by sensors measuring its every movement. And still it keeps its secrets. Not because we are not looking closely enough, but because some systems are fundamentally unpredictable beyond certain timescales. We live on a geologically active planet. Volcanoes will erupt. Earthquakes will strike. Despite our best instruments, our most sophisticated models, our centuries of accumulated knowledge, nature operates according to rules that we can observe but not fully predict. Axial Seamount will erupt. Maybe in 2026, maybe in 2027, maybe tomorrow. The sensors will record every second. Scientists will analyze every data point. And humanity will learn again that understanding a system is not the same as controlling it. The world's most monitored volcano has taught us humility. The question is whether we will remember the lesson when the next Vesuvius, the next Krakatoa, the next Tambora begin showing signs that we think we understand. 300 miles off the Oregon coast, 1,400 meters below the surface, Axial Seamount sits primed, monitored, waiting. Not for us to predict it, but for us to accept that some things, no matter how closely watched, remain beyond our grasp.